The idea of how much dissipation should we introduce again comes from upwinding. So let's actually discuss upwinding a little bit more. So if we have a numerical solution du dt plus partial, let's use w, partial fw partial x equal to 0. Okay, and let's first consider the case if fw is equal to u times w. It's a linear equations. All right. The upwinding for this case is dwi dt plus u times two cases. It's either wi plus 1 minus wi divided by delta x, or dwi dt plus u wi minus wi minus 1 divided by delta x equal to 0. And this choice is dependent on what? Dependent on if u is positive or negative, right? So this is when u is so this is upwinding towards the right, which means the wave has to be coming from the right, and that's the case when u is less than 0, and upwinding towards left happens when u is greater than 0, right? Okay, but it's interesting that both cases can be written in a slightly different way. So when u is greater than 0, for example, wi minus 1 divided by delta x can be written as the central difference plus a correction term. And the term you would correct this is so let's actually figure out what's the correction term you would add onto the central difference to make it a left upwinded scheme. Okay, to make it on the right, you would actually have 2 delta x, something that is actually you have to get rid of this, right? So which is minus wi plus 1, and then you have to form wi. So you have to get 2 wi's because this is divided by 2 delta x. So you have 2 wi, and then this is only 1 of wi minus 1, and you have to make 2 wi minus 1s to counter for the fact you have a divide by 2 over the right hand side, and you don't have divide by 2 on the left hand side. So you have to minus wi minus 1. So what does this look like? This looks like a second order derivative, right? So basically you have to plus a negative dissipation to make it the same as the upwinded scheme. So this is saying that alternative to write this down is dwi dt plus u times the central difference scheme plus, we have to have a u here. Oh, sorry, let's say just equal u times 2 delta x wi plus 1 plus wi minus 1 minus 2 wi. So this is like a second order dissipation scheme. Okay, when u is less than 0, well, in order to make this scheme here, let's try it again. Wi plus 1 minus wi divided by the xi. How can you write it as another correction term from this central difference? Well, we can do the same. First of all, we have to make another wi plus 1, right? And we have to form minus 2 wi's to count for this term, and we have to get rid of the wi minus 1. So we have to plus wi minus 1. So the effect is that I have added a second order derivative instead of subtracted a second order derivative. So the result is that dwi dt plus the same central difference operator, but I have a negative sign on this because okay, so but both equations can be written into the same equation, which is dwi dt plus the central difference equal to the absolute value of u, right? Because this is when u is negative, this is when u is positive, times the second order derivative. Now this makes total sense, right? Because I need to add a positive numerical dissipation on the right hand side to make the scheme stable, right? So no matter if I upwind towards the left and right, the effect is exactly the same. I'm adding a positive numerical dissipation. And the key point is how much numerical dissipation I added is actually the absolute value of the wave speed. It's the absolute value of actually the derivative of f with respect to w. If the wave travels faster, I need to add the more numerical dissipation. If my wave travels slower, I add less numerical dissipation.